Hi, uh, hello and welcome to the introduction video of structural theory. So this is our reference for this subject, this course. So we might as well try to get uh, access to this book. So in this chapter, the subtopic will be introduction, classification of structures, loads, and structural design. So structures refer to a system of connected parts used to support load. So main objective is support load, and then it's being built by many parts. And structure can be defined in the form or shape, such as building. So building is a structure, bridge is a structure, dams and walls, like retaining walls. So basically to resist load, to apply load, to carry load. And by carrying the load, uh, the strength capacity is not losing. The structure is not losing its own strength capacity or any appreciable deformation. There's no like major deformation that will alter the trajectory of the forces acting on it. And the fundamental purpose of the structure is to transmit all applied loads to the point of support system, and basically to the foundations, to the ground. For example, you have a building here, multi-story, and then you have column in the middle. So you apply load here, people walking, people working inside of building. So the load will be transmitted from the slab to the beam and then to the column and up until the foundation of structure. So basically, the structure will be supported by the foundation. And factors to be considered is safety of the structures, the look of the structures, and then how long it can serve you without any loss of strength capacity or any deformation, and then the economic value, the cost of building it, and then the effect on the environment. Next, we take a look at the classification of structures. So, classification of structures, we can there's a structure elements in a structure. So, structure can be made of tie rods, beams, and columns. So, these are structure elements. Tie rods is when the a rod, a member uh, being applied axial load at both ends. So usually being used to make truss. And then you have beams such as this, and then columns, the vertical member of structure, vertical element of structure. And column can also exist as a beam column when you have a moment acting at the end of uh, column. And then types of structures. So these structure element combines become a structure. So the type of structure can be classified as trusses, cables and arches, and then surface structures. Next, let's talk about loads. So loads, when you apply loads on a structure, the loads is applied onto the structural forms, the form of structure. So the load applied on form of structure, and then the load goes into the elements carrying the primary loads. So the elements, as we talk about, either it's trusses, columns, beams, so the loads goes through the column to the beam, and then the various supporting members, and lastly towards the foundation at the bottom. And design loading for structure is often specified in code. Usually when you follow codes, there's a design loading given by the code, so you can follow to estimate your loading, the loading of your structures. And you have, for example, in this book, it will be heavily referred to the SCE design codes, which is the American Society of Civil Engineers, in section of minimum design loads for buildings and other structures. But you also have another design codes, ACI, American Concrete Institute, and then from structural side, steel structure, American Institute of Steel Construction, and then for road we have ASHTO, American Association of State Highway and Transportation Officials, And then from FPA for timber structure, and then from American Railway Engineering Association for railway. And in Malaysia, we follow British standard, we follow Eurocode. And then let's take a look on type of loads. So type of loads, there are only two type of load. Dead loads, live load. Dead loads, as the name implied, static load, load that doesn't move. So dead loads carries the weight of the structure members. As we talk about previously, you have tie rods, beam, column. Sometimes your columns made of steel structure, a steel material. So that is the density of steel for that structure becomes the dead loads, the weights of your structure members. And also dead loads refer to weights of any objects that are attached to structure, any objects that is permanent on the structure. So in ASCE design code, given you the material and then the density. Okay, so when you times the density with the length or area, so you get your load, kilonewton. And also in the ASCE design code gives you the loading from walls, dead load from walls, floor filling, ceilings, and frame partition walls. So this is given to you in kilonewton per meter square per area. So you times the area, you get your load. Let's take a look on example of these loads. So the floor beams is used to support the 1.8 meter width of lightweight plain concrete. So your beam here, I beam, to carry a 1.8 meter here length of plain lightweight concrete slab with thickness of 100 mm. And then the slab serves as a portion of the ceiling for the floor below, and its bottom is coated with plaster. So you have a plaster here, plaster plaster here below the slab, below um, the beam. And then you have a 2.4 meter high concrete block with 300 mm thickness directly on top of top flange of the beam. Top flange, as this picture shows. So how to calculate load? The first thing, maybe you start with concrete, the slab. So it is a concrete slab. So the concrete slab is 0.015 concrete here, concrete uh, using 0.015 concrete slab, lightweight concrete plane per millimeter. So this is your dead load from slab times by the thickness and also the length. So you get your load per meter for concrete slab. Then you have plaster ceiling below the slab. So you plaster ceiling is given here on ceiling based on loading from ASCE. Ceiling plaster on tile or concrete 0.24 kilonewton per meter square. So this is given by the codes. Times with the length, then you get per meter 0.43. And then block wall of 300 mm clay brick. So you have 5.51. Or this one is another type. So for the wall, since this is not a clay brick wall, this is a lightweight solid concrete, so we use the density of lightweight solid concrete, so it is 16.5 times the length and the thickness. You get this value. So total up this value, you get this total dead load acting on a beam. So next is live loads. So live loads varies in magnitude and location, and then you also have uh, live load from building loads, which depends on the purpose for which the building is designed. So these loadings are generally tabulated in local, state, or national codes. So given in codes, if you're referring to ASCE, so uh, this is excerpt is taken from the ASCE design load. So so as you can see here, the live load depends on the type of area used for that building. For example, uh, uh, there is a fixed seat, or if it is a movable seat, so a fixed seat usually in stadium, for example, in a hall. And then if it is an office building, so the lobbies will have this higher load compared to offices unit will have a lower load. If it is a warehouse, if it's a warehouse, so if it is a light warehouse, then the life load will be lower compared to a heavy warehouse. And for residential, if it is a dwelling landed, so this is your load, which is similar to hotels. But if it is a public rooms, like common rooms and corridors for hotel lobby, or common area for in the hotel, so the code expect heavier loading. Hence, you can see the value going higher. This is for school, so you can refer back once you start designing. Next is a structure design. Material uncertainties occur due to a variability in material properties, residual stress in materials, intended measurements being different from the fabricated sizes, and material corrosion. These are some of the material uncertainties that can occur during the construction. So many types of loads can occur simultaneously on a structure. So in working stress design, the computed elastic stress in the material must not exceed the allowable stress along the following typical load combination as specified by ASCE 710 standard. So to compensate for these uncertainties, and then the loads occur simultaneously. So in ASCE, this is the safety factor for that load. So you have 0.6 times dead load, and then 0.6 times wind load, or you can have 0.6 times dead load plus 0.6 times earthquake load. In strength design, material uncertainty and load uncertainty are separately determined. So this method uses load factors applied to the loads or combinations of load. So 1.4 times dead load, if you have dead load and a live load and a snow load, so 1.2 times dead load, 1.6 times live load, and 0.5 times no load. So basically this is the safety factor lah. Instead, you have actual dead load you calculated, then you add 0.2% more, which is 20% more load from the dead load. So basically you are designing for 120% dead load, 160% of live load, and then 50% of snow load, because the codes expect that the occurrence of load from the snow will be um, not that frequent. It depends on the structure, so it can reduce the factor of snow load. Um, if it is a combination of dead load and wind load, and this is the safety factor, and then this is a combination of dead load and earthquake load. So the safety factor is reduced, because yeah, the chances of the load acting, like wind load acting on the structures, depends on the weather, depends on the season, and also earthquake load is dependent on the chance of earthquake having in that area. So the chances differs. So most of the time, the load acting on the structure will be from the dead load. But once the earthquake occurs, so there will be combination of these two. So that's why the code able to reduce the safety factor from that load, because we are designing for these two types of load. So the loading will be heavier. So that is all. Maybe we can recap what we have learned from this video. The first one is the safety factor. Start from the bottom. Safety factor that apply on the load, because the uncertainty of the load acting on the structure, and the uncertainty, and also the uncertainty for the material side. We have uh, low quality material that side, problem or error occur during mixing, or some shoddy work. Compensate that, the codes introduce the safety factor, or the multiplier for your loads. Then we talk about live loads. Live loads come from your, you can refer from your design code, give you based on the function of your building, whether it is a stadium, office building, a storage warehouse, or residency or school. And then where you have dead load, so this is how you calculate dead load, also given by your codes. Basically you can refer to your codes, how the value given by the code, so that your design is in compliance to your code. So this is example from ASCE. So this is your dead load that can come from your structure members, and also come from the object attached to your structures. And then we talk about the loads, and then how loads being transmitted um, towards your building, start from the top, loads acting on structural forms towards your elements towards your structure, and then the supporting members, and then lastly towards your foundation. So we also talk about the type of structure elements. You have tie rods, beams, columns, and then type of structure you have trusses, cables, and arches, and also the surface structures like such as dome, or like spherical water tank you can see on the roadside. We also talk about what is structure. So structure is a connected parts that is designed to carry load without losing its strength, capacity, or any deformation. And you also have to consider this in your design of structure. And that will be all. Thank you for your attention, and see you in the next video.